Today we are getting into what I would consider of all major commonly used scientific diagrams in terms of like graphs of information. Um, this may be the one that has the most information on it. Okay, of commonly used ones. Um, Again, this is comparing to like the graphs that we've done before. Again, think back to the beginning of the year. We had like the position versus time graphs, the velocity versus time graphs. Okay, what could you figure out from those? You could figure out a decent amount of, position stuff like that. Um, there's also stuff involving waves. Like again, think like the black body radiation. There's that kind of graph, right? So these are commonly used graphs that we use, and I'm not even talking about just physics, by the way, with that statement I made before. This again, in terms of commonly used scientific like graphs, and this is not like infographics, right? I'm not talking about those. This may be the most dense. So your warm-up question is simply list all the properties that are shown on the diagram. But what is the diagram? Diagram is known as the HR diagram, which is an abbreviation for someone's names, two people's names actually. So the name's not that important, but it's a diagram for plotting stars. This is the diagram. This is the diagram. So stare at this and really think about what are all the things that this diagram is showing us. Okay, don't like draw any conclusions about the data. Okay, don't think about like, well, because of this, this diagram says this. No, I'm just talking about just on a bare base level, what is on this diagram? What properties are shown on this diagram? Okay, all of these are stars. Okay, all of these things on here are different kinds of stars. So how are these stars being plotted on this diagram? What are different labels and variables and stuff given on the diagram itself? Okay, think about this. There are several. Okay, so really think about this for a bit, and then we'll list out what you can find and what you can notice, and then we'll come back and look into this. All right, now the first thing you probably want to do is to check the axes of this graph, right? It is a graph, so it has something on the axes. Now, it actually, in terms of the labeling here, we have three axes to look at, right? I mean, there's the y-axis, but they're labeled differently. But let's look at the x-axis first. So what's the x-axis? The x-axis is surface temperature in Kelvin. Okay, so that's one thing that it lists. It lists surface temperature. Okay, so we have surface temperature in Kelvin, if you want to put it that way. Now, notice something weird is that it actually increases this way, right? These are the higher temperatures, 30,000, 20,000, then 10,000, 7,000, 6,000, 5,000, 4,000, 3,000, right? So for some reason it's reversed. I don't know why that it's done like that, but it is. The rule for this is that for some reason temperature is on the x-axis, and it's always plotted so that the hotter temperatures are on the left. I don't know why, but that's just how it's always been and with this kind of stuff, and so there we are with that. There are also these red things here, which you notice says spectral class. Now we'll kind of explain more about this as well, but that could be something you talk about. Well, it mentions spectral class. I don't know what spectral class is necessarily, but that is something, so we can put that in as well. And it has something to do with these red, A0, A5, F0, F5. What does all this mean? And you may notice also, hey, this is O5, this is O5, B0, B5, A0, A5, F0, F5, G0, G5, K0, K5, M0, and M5. Notice the letters O, B, A, F, G, K, and M, right? O, B, A, F, G, K, M. Okay, so these big yellow letters are related to these. Okay, so that's related to the spectral class kind of stuff. Okay, so let's look at the over here on the left. We have absolute magnitude, and it says brightness. So I'm just going to say magnitude. Now, I think I mentioned this at some point. I don't remember. But the magnitude scale is a way of measuring, again, how bright something appears to be. Absolute magnitude is basically saying it is the actual brightness of the thing versus just relative magnitude, which is basically how bright does it look to me. Okay, so for example, I could say, well, the sun, if I have a light bulb right next to my face, I could say, oh, it's brighter than the sun, right? Because like it is compared to me, for me technically, but like absolute magnitude is a way of counteracting that. So for example, a star that's really big and bright, it could be super far away, so but so therefore it does not look as bright as something that's smaller but closer, right? But the absolute magnitude counts for that. Now this scale is dumb. Okay, so first of all, notice as you increase in number, you go down, and also notice you have negative numbers up here, and then also 0. You might think like, well, I mean, how we standardize it with like the sun maybe. And the sun, if you can see, it's actually right here. It's hard to see, but if you zoom in, you can kind of you can see it a bit better. So the sun is not at 0; it's at like +5. So magnitude scale is dumb. Basically, it's like, I believe the magnitude scale is so that 0 on the magnitude scale is the star Vega, which is Vega right there. 0. Yeah, it lines up anyway. So why Vega? I don't know. Okay, it's a way of measuring brightness. I don't like it though. So there's that. Now over here we have luminosity, and this is in suns. So luminosity we've talked about before. So luminosity is measurement of how much energy is being emitted by the star, and so that ends up leading to brightness, right? The more energy that it's being emitted, the brighter it appears to be. So the magnitude scale is basically talking about brightness in terms of like our eyes and our instruments observing a thing, whereas luminosity is talking about brightness in terms of the actual thing emitting the light. Okay, and luminosity is, I think it's better in terms of physics anyway, because it's talking about like energy production of a thing. We've already kind of talked about that. So to me, I always use luminosity when I'm talking about the brightness of a star. And how this is measured, this is in suns. This is saying it's measured in solar luminosity. Okay, so in solar luminosity. So what this means is that this is where it is standardized that 1 is the sun. Okay, so the sun is 1. So 0.01, that means any star that's right here is 1/100th as bright as the sun. You would need 100 of these stars to look to be as bright as the star. Down here we're at 10,000, and then down here we're at a billion? A millionth? No, that's 10 millionth all the way down there at the bottom, right? Yes. So the scaling's a little off for some reason. But yeah. And then up here we have 100 times, so any star that's up on this path is 100 times brighter than the sun. Up here we're at 10,000 times brighter than the sun, and I presume up here there's like 1,000,000 times brighter or whatever. So yeah, that's a bit better way to kind of measure it. So that's what we have there for that. Okay, so that's the axes. But we're not done. There's a couple other things that are shown here. One of which you may have noticed is that there are these sort of, this is hard to see, but there's this like arc right here. There's also one that's like right here, and one that's here, and here, and you can see there's this arc, and you can see there's this text right here. So let's see if we can zoom in and read it. It's hard to read. 0.001 solar radius, 0.01 solar radius, 0.1 solar radius, 1 solar radius. This up here, this one's 10 solar radius. There's 100 solar radius. And up here we have 1,000 solar radius. So these lines are describing the radius. Okay, so the radius is measured in solar radii. So again, it's compared to the sun. And you'll see here, we have these lines of constant radius point to these lines. So that means any star that would fall on this line would be exactly 1/10 the size of the sun. So there isn't really anything on this line over here. But when we get over here, so any star that's right on this line would be 1/10 of the size of the sun. Okay, it's 1/10 of the size of the sun, but you can see the brightness is scaled a little bit differently, right? So it's not how that works there. And so also this means any star that's aligned in here has the same size as the sun, and there's the sun right there. So you can see, for example, a star that's here, this star is the same size as the sun. It's on this 1 solar radius line. However, it is a little bit dimmer, and it's colder. Okay, so that's something that you can kind of get in with that, and how you can see how these are not, even if it's the same size, but it's not exactly the same because of other methods. And any sun that's up here is 10 times the size of the sun, so is that Capella's pretty close. Anyway, it's hard to tell exactly. And then 100 times up here, something like Gamma Crucius is kind of up here. You can see the names of a bunch of stars. Anyway, 1,000 times you get to stuff like Betelgeuse, which that's, yes, you say that is Betelgeuse. That's the star, if you ever heard about, there's a star that we think like that's like pulsating weirdly and like might go supernova soon. That's the star that we're talking about. Yeah, so Radius is something that's on here as well. There's others, but we've still got more to go. For one, and you might not even thought to think about this at first, but shows color. Okay, this shows color. We have blue stars over here, and then we have kind of white stars here. We have yellow stars, orange stars, and red stars. Now, I think I said this to all of my classes, but the sun is actually white. It's actually not like yellowy orange. It's actually a white star, so this is not actually like perfectly representative of the color. If anything, it should be sort of, all of these colors should be shifted over more, so the sun is white, and then like these are yellow, and these are orange, and only these ones are red, and like blue kind of makes sense wherever. But anyway, the rough outlook of everything is similar. It has to do with sort of peak wavelengths as well. So yeah, so this is why if you hear the sun described as a yellow giant or like a yellow dwarf, as a yellow dwarf, and you're like, well, but you said this, so the sun was white. It's nomenclature how this works. So if I refer to the sun as being a yellow star, it's technically not, but it is in terms of classification of stuff. So anyway, but yeah, it shows color. There's two more things to look at. Actually, no, one more thing. Sorry. For some reason, I think we hadn't talked about size, but we did talk about size. And this one is also hard to see, but you can notice it shows rarity. Okay, how common stars are. For example, you'll notice, just look at sort of this group of stars over here. There's not that many of them, right? I mean, right here, there's like 1, 2, 3, 4, 5, 6, like 6 stars in this sort of group right here. Now, does that mean there are only 6 stars that look like this? No, right? There's billions, but it's comparative, right? So there's only 6 stars here, but if I take the same sort of sample over here, there's a lot more, okay? There's a lot more stars over here. So this also shows generally how common stars are. So I'll describe it as rarity. And so I think that's everything. Yeah, there is one more thing that actually is there's 2 more things that are related to all of these things, but they're not explicitly shown on the diagram. You can sort of infer what they are from that. So that's something. So what is this? Okay, so this is known as the Hertzsprung-Russell diagram, or HR diagram, and it is it's a diagram, can't type, that categorizes stars by temperature and brightness, along with other properties that fall from those. So, in other words, again, for example, radius, spectral class, the color, all of that is a consequence of the temperature and luminosity. And so that's how they're kind of define that. So a pure HR diagram, again, if you were to Google this, for example, they all will have temperature and brightness, luminosity, whatever, on the axes. The other stuff is sort of extra stuff you can add on top of it. That is important, but the definition of it is this is a diagram when you plot all the stars you see in the sky based on their temperature and, again, either their magnitude or their luminosity, depending on which one you're looking at. But again, they both measure brightness. So, what does this show? This, again, shows us that we have several ways of categorizing stars. Now, there's a few things to notice. Some of these properties, you notice, are related. Okay, for one, you notice where are most of the stars in terms of like a section of the graph that has the most stars. Now again, most of them are over here, but this whole kind of chain is like where most of them are, right? Most of them follow this sort of chain that kind of, it's not a perfect diagonal, right? It sort of slopes down and then it kind of gets flatter, and then it goes steeper again. But you have this sort of line that covers this sort of diagonal here. That's where most of the stars are, somewhere on this line. Again, they're not perfect. It's not a perfect line, right? There's like this one's kind of a little bit below it, and this one's like a bit above it or whatever. But, you know, they're close, right? Then you have a decent number of stars sort of in this kind of cluster. Notice here it says white dwarfs, kind of pointing to these stars here. This also says main sequence. So this line here is known as the main sequence. Okay, so the main sequence of stars. So when I refer to in main sequence stars, or if I just say stars, I'm often just talking about main sequence stars. I usually will specify if I'm talking about a different kind. So for example, here, these ones over here, and this also extends to these other ones up here at the top. It says giants and supergiants. Okay, so these are kind of your main categories of stars in this sort of layout. But yeah, most of them fall under this main sequence, which is this sort of this line here in the middle. But you also have this spectral class, these sort of letters, these O, B, A, F, G, K, M. Now, you may wonder kind of what these names come from. These letters actually originally came from, I believe it was how bright the helium spectra shows up in the star. If you like were to look at its light and spread it out, you know, like we talked about for the atomic spectra stuff. I think that's what it is. So A stars have the strongest helium, then B have the next strongest, and they sort of categorize it where like B is like, I don't know what the number is, but let's say it's like one step below A, and then a C star would theoretically be one step below B, but no stars look like that, basically. And so then a D star would be theoretically one step below a C, but again, no stars like that either. And then so basically there's no stars until you're, C, D, E, until you're 4 steps below a B, and then like, oh, then you get F stars. A step below that, you get G, and then H, I, J. Okay, you need 4 steps again to go down to K, and then 2 steps to go to M, and then 2 steps to go to O. Okay, so that was sort of how that came to be originally, but it's sort of been refitted because, you notice the letters are out of order, because it makes more sense to sort of categorize this in terms of temperature. Okay, so spectral class directly relates to temperature, and how that lines up there, and you can kind of see how that works. So, for example, a star that is 4,000 Kelvin, or let's just see 5,000 Kelvin. 5,000 Kelvin stars, you see how this lines up with the K0, and again, I'll explain what the numbers are in a second, but basically, if you have a 5,000 Kelvin star anywhere right in here, it is considered a K star. Okay, actually between 5,000 and 3,500, if you have a star with a surface temperature between those two temperatures, you are a K star. Okay, so anywhere in here, even if you're a giant up here, you're still considered a K star. Meanwhile, if you're below 3,500 in terms of your surface temperature, you are an M star. Again, even like this giant thing up here, it's going to have below that temperature, it's going to be considered an M star. It would be an M giant, or M supergiant actually, they're really big ones, whereas these it would be M main sequence, or sometimes referred to as just M dwarfs, or just red dwarfs. But that's sort of the range there. G stars, again, anywhere between about 6,000 and 5,000. Temperature is G star. You can see the sun falls under this range. So the sun is a G star. You could also a G main sequence. You can also have, G giants as well. F stars fall between, the scaling it's a bit weird. I think it's about, I think it's like 7,500 to 6,000. I don't remember. Anyway, F stars, anywhere in any kind of star in here is considered an F star. Any star from about 10,000 to, say 7,500 or something is an A star. Anything that's between about, I think 25,000 and 10,000 is a B star, and then hotter than 25,000 is an O star. So that's sort of been how it's co-opted. Again, you don't need to memorize like the numbers for this. I'm just sort of giving you an idea of how this works. So if I tell you, hey, a star is an O star, you know it's somewhere in this sort of far left band. You don't know if I just say it's an O star, it could be this one here, really tiny one. It could be this 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 one. You don't know if I just say it's an O star. For example, also if I say, oh, it's an A star, it could be this one, it could be this one, it could be this one, it could be this one. You don't know, okay? But it is one of these in here. And again, if it's an F star, it's one of these in here. If it's a G star, it's one of these in here. K star, one of these in here. And M star, one of these in here, right? And these stars are very, right? This star, Mu Cephei, is very different than Proxima Centauri, right there, okay? It's very different. Obviously, the size is going to be very different. The brightness is very different. But the temperatures are about the same, okay? So the letters correspond to just the temperatures. The letters tell you what region on the x-axis is the star going to be in. Doesn't tell you anything about the y-axis. Now, one way to remember the order of the letters is through a mnemonic. So let me actually kind of write this out for a second, though. So spectral class is based on the surface temperatures of the star. Which will determine whether the star is an O, B, A, F, G, K, or M star. Yeah. And then I'll clarify also, it doesn't matter how big or bright the star is, the letter is only determined by temperature. Now it is. Again, originally it was all about helium lines and stuff, but it's been co-opted to be about surface temperature. The way to remember the order is the saying, and this was taught to me when I was doing astronomy stuff in college. O, be a fine girl or guy, whichever one you want, and kiss me. That's the statement, okay? O, be a fine girl and kiss me, or O, be a fine guy and kiss me. So, see, it's inclusive. And there you go. I'm sure there's something else you could come up with if you really want to, but whatever. But that's sort of the thing. And again, I use the ampersand for and, so you don't get confused that, confused about that. So, yeah, that's the saying. Oh, be a fine girl and kiss me, or oh, be a fine guy and kiss me. Yeah, there you go. Now, you may notice, though, especially when you get down here, that there's these numbers that are kind of after the letters. Okay? So the numbers, the spectral classes are divided further by numbers from 0 to 9. Okay, let me just smooth that down. So within each letter, let's see, that makes it go back. So, okay. With 0 being the hottest of that letter, and 9 being the coldest of that letter. Okay, so this means the hottest stars would be an O0, right? It looks kind of weird, but that's the hottest. And then followed by an O1, and then an O2, then an O3, and an O4, O5, O6, O7. These are all getting colder as we go to O9, and then the next coldest one after O9 would be a B0. Okay, and then B1, and then dot dot dot. It keeps going, right? And so then also the coldest stars, yeah, let's kind of extend on where we were going here. Let's see, K8, K9, and then we go to M0, M1, M2, M3, M4, M5, M6, we're going to space, M7, M8, M9. Oh, I didn't know space. So an M9 is the coldest star, and O0 is the hottest star. Okay, of the main types of stars. There, you can actually extend this past M and to get to even colder stars with like brown dwarfs and stuff, but those are like not full stars. Again, we'll talk about those more later, so don't worry about those for now. So it's just further subdividing the letters here. So don't worry too much about the numbers. They're basically, again, they're a way of narrowing in on where along the x-axis do you fall. Okay, so again, an A5 could be this star, or it could be this star, right? They're both very different stars, clearly, because they're, one's way brighter than the other, one's way bigger than the other, but their temperatures are going to be in the same sort of much smaller range than just A. So they would both be A5 stars. The sun is a G2 star. Okay, so the sun is a G2 star. Okay, so that's where it falls into place in terms of the lettering. Now you'll notice also, for example, Alpha Centauri, it's noticed it's a little bit above the sun, so it's a little bit bigger, and I believe it's a little bit hotter. It's very close though, and so even though it is a little bit brighter, it is still considered a G2 star because it is in that sort of layout. But we need more than just that, right? For example, you could say, okay, the sun, sure, maybe you might agree that, okay, the sun and Alpha Centauri, they're probably close enough that you can classify them the same way. Fair enough, I'll buy it. But like this star, even if it's like maybe a G2, like there needs to be a way to differentiate this star from the sun. And there is. Okay. And so this is the last part of the classification. And it's that, so we have the letters, we have the numbers, and then we have Roman numerals. Tell you which part of the HR diagram the star is on based on its size and its age. Okay, so, and again, we'll get to the different kind of spots on the life cycle of where they are when we get to that. So there's kind of a some expansion in terms of the Roman numerals, how that all work, but generally there's this normal one is just using 1, 2, 3, 4, and 5. Okay, those are generally the Roman numerals that are used. Excuse me. And so let me actually pull up the Wikipedia article for this. That was weird. It didn't register that. HR diagram, because this one has actually a good line of that. There's someone. Here we go. I kind of wanted it if it's not labeled like that, but it's fine. Actually, this is not what I wanted. I know. Hold on. Done. And then I can click on. So if you ever type in a star, we see spectral classification. So here, for example, sun has a Roman numeral 5. So we'll get to what that means in a second. But here's what I want. Okay. So this is the image I wanted. Now this here, you'll notice again, like for example, there's a 0, there's 1A, 1B, and then there's like 6 and 7. So don't worry about those specifically. The ones that we care about is 1, 2, 3, 4, 5. Okay, those are kind of what we want. So let's start with 1. 1 is often is basically the hypergiants. Those are the biggest stars, and those are the ones who are basically at the very top of this sort of region here. So these very biggest ones are 1. So again, this of course is a really giant one. Eustathiae, Betelgeuse, Antares. Polaris was labeled on here. Oh, that's Polaris. Polaris, I think is a 1. It might actually be a 2. Anyway, but definitely Deneb. Yeah, these are 1s. So 1s are hypergiants. They are the biggest kinds of stars. So hypergiants, biggest stars at the top of the diagram. Okay, so for example, if I had, going back to the star here, maybe, again, this big one right here, maybe that's if we go straight down, like a G, I curved all through that, G4? G4, let's say G4. So this big star here would be a G4 Roman numeral 1, okay, or G4I, if you want to call it that. So that would be a G4 1. Let me look way of classifying that. Mu Cephei here, that would be, again, also a hypergiant. So that would be like a, I guess, M5 1? I'm actually not sure what it is. Let's look that up, actually, because we can go back to that. Let's see. Again, we can look this up. Mu Cephei. Vector class. Okay, M2, again, there's some letter, there's the 1A. Again, don't worry about the 1A. For the Roman numerals, and I'm actually not sure what the E is. Probably has to do with how it was formed? I'm not sure. But yeah, so this M21, okay, that seems to line up pretty well with what we got here. M2, let's see, whatever. So, close enough. So yeah, that's kind of what those are there. So, that's that. Roman numeral 2 is kind of a little bit weird. Actually, I'm going to skip Roman numeral 2. I'm going to go to Roman numeral 3. Roman numeral 3 are the giants. Okay, so these are big stars that are what's the word? Grouped above the main sequence. Okay, so going back to here. So for example, these are kind of your threes. They're kind of grouped with the main sequence. You can set others. So like again, this one I'm not sure. Again, like Polaris, I'm actually not sure. But mostly these are generally the threes, because there's even if a grouping could exist, there's often not that there. For example, like there's like no star like right here. For example, I could have that would be like a B5 Roman numeral 3, for example, could be like right here. You could have a star that is there, but there are not many of them, and the reasons for that have to do with how stars change over their lives and stuff like that, but which we'll get to later. But the classification is there. So generally, you have this kind of line here, and you can see. Here's the threes. You have this sort of categories that kind of it sort of sits above the main sequence in this sort of line here. So threes are the giants. Now, and I'm also going to skip Roman numeral 4 and go to Roman numeral 5. This is the main sequence stars. Most stars fall into this category. Okay. And again, sometimes these are just referred to as dwarfs, even though they're not like, again, the sun is this, so it's not, the sun's a dwarf. Well, I mean, compared to like these, sure, but so basically anything that's in this line is a 5. Okay. Now notice that doesn't mean that it's in the same position on the y-axis, right? So this star up here, Achernar, it's in the main sequence. So it would be I don't know what, B3, B4, V. That's definitely, it's a very different star than, again, Proxima Centauri, which would be like an M5V, right? But they are still both in the main sequence. And again, the reason for that has to do with, again, how the stars develop and change over time. And we'll talk about that tomorrow. But just keep that in mind. So if you see a V as the Roman numeral for a star, it's somewhere in this central main sequence. Okay, and then where specifically it is going to change, depending on the letter and the number. Now, again, note Alpha Centauri and the Sun, they both would have the same sequence, because, again, I said they're both G2, and that tells you your X component, but they're both in the main sequence in this spot, so they would have Roman numeral V. Same with the star that's up here. Now, this star, for example, that's above Alpha Centauri, it's, probably has maybe like 10 times brighter than the sun. So it's a star that's 10 times brighter than the sun, and it's noticeably a bit bigger than the sun, but it has the same classification because it lines up not only in the same sort of left and right position, but it is still a main sequence star. So keep that in mind. So then the question about 4 and 2, these are sort of your midpoints. So if a star is like kind of halfway between a hypergiant and a giant, it's a 2. And these are sometimes referred to as bright giants. So large stars between giants and hypergiants. And similarly, a 4, I've seen referred to as subgiants. So, fairly big stars between main sequence and giants. Okay, so again, these are sort of your between ones. So a 1, again, so the 1, these are the stars at the very top. Those are the really, really big ones. a 3 is sort of it's this usually this branch over here and then also kind of leaning up towards here, and then a 5 is this whole stretch down here. And so a 4, for example, like some of these might be 4s, like maybe this one, maybe this one. But like I know, for example, I know Pollux is a 3. So again, it's not just where it falls in the diagram. It has to do again with where they are in their life cycle. And again, 2s is where things also get a bit complicated. For example, I think I know Betelgeuse is a 1. I know Antares is a 1. I'm pretty sure Mira's a 3. I guess it might be a 2. I don't know. But see, again, it's hard to tell exactly. So don't get hung up so much about like this. This is like a coordinate system for the diagram. It's not. It's basically a way of fitting the classification scheme to the diagram that already exists. So, and especially because if you see this image here, for example, notice all of these lines sort of converge like when you get over here, right? So it's like, oh, if I have a star like right here, I guess it falls under a 2, but if I'm like slightly off, then all of a sudden I'm on a 1. So it's like, it can be hard to sort of piece that out. So don't worry too much about like being very precise about it. But just remember that the letters, you see this extends further past M to L and T, but don't worry about those. These are when you get into things that are like not quite actual stars. Just think about, okay, the letters and the numbers tell you where horizontally the star is. So for example, again, G2, and if I get a G2 4, well then I'm going to find the main sequence kind of about where the G2 would be, and then just go a little bit above that. Okay, so again, I would go G2 sort of here, and then the main sequence would go a little bit above that. So I'd put a star, it's a G2 4, Roman numeral 4, here-ish, right? But again, a G2 Roman numeral 3 would be just slightly higher than that. So it's not perfect, okay? It's not super precise in how this works, but that's sort of the manner of how this goes about. You might wonder, well, what about all the stuff down here? Now, this diagram, it's sort of, again, the expanded one, we have a sort of a 6 and a Roman numeral 7. The 6 is, again, sort of like, you just have the 4 is like, well, go to the main sequence, go slightly above it. The 6 is sort of go to the main sequence, go slightly below it. So that would sort of qualify as like, probably this star would be like a 6. I'm not going to really talk about the 6s, so don't really worry about that. The 7s are basically saying any of these other things, the white dwarfs and stuff like that. I usually don't use that either. I just will tell you it's like a white dwarf. So for example, I would say this star is an A0 white dwarf. Okay, and I don't even use the Roman numerals, but sometimes you see Roman numeral 7 or whatever, so it's just, whatever you are used to seeing with that. So just to keep them out. I'm not going to use the 7s. I'm just going to use 1, 2, 3, 4, and 5. But you could see that if you're looking into this more. So, yeah. Again, so that's sort of the classification of how this works, and we'll practice with this to kind of see how we get used to this a little bit more. But I want to kind of extrapolate what we looked at. Let's just look at the main sequence by itself. Okay. So, and again, main sequence. These are sort of most of the stars are again anything on this line here. And let's sort of look at on one end we have the O stars. Okay, so we have O stars on one end and M stars on the other end, right? And so let's look back at the warm-up question. And so what are all the things we had? And let's sort of like look at each of these properties and how these work. So let's see, for the main sequence, surface temperature, okay? So the surface temperature for the main sequence O stars, so all the ones all the way over here, that's going to be about as hot as a star is going to get, 30,000 or so. That's about as hot as they're going to be. So these O stars are the hottest. The M stars are all the way over here. So their surface temperature is going to be the coldest. Okay. Next we have spectral class. Well, that's already dealt with in terms of the O's and the letters, so we don't worry about that. Magnitude and luminosity, those deal with brightness. So in terms of brightness, well, again, in and of itself, it doesn't have to be the same. For example, like this star right here is gonna or let's say this one, this O star here is gonna have the same brightness as like this M star here. But these are not in the main sequence, right? These are in this white dwarf section below the main sequence. So comparing any O star on the main sequence to any M star in the main sequence, the O stars are brighter. Okay, so of the main sequence stars, the O stars are the brightest. M stars are the dimmest. Let's see again, main sequence. Next up we have the size. Okay. So in terms of size, again, you can So notice how the lines of conservation. So again, as you go, the smallest stars are down here, the biggest stars are up here. So the biggest stars, in general, are the M stars. They're these M hypergiants. But of the main sequence, you can see how the line works. So the O stars here, they are kind of above this line, the one solar radius line. They're all above it. They're all bigger than the sun. Whereas the M stars here, they're like, some of these are less than like a tenth of the size of the sun. Some of them are down like a hundredth the size of the sun. So of the main sequence, the O stars are the biggest. M stars are the smallest. Let's see. What do we have next? The color. Well, okay. I mean, O stars are the bluest and M stars are the reddest. So I guess I'll put that in there. Okay, so where are we at now? Oh, and then rarity, again, we can see from the image here. There's a lot more of these M stars down here than there are O stars up here. And there's a couple, so for example, so the O stars are the rarest, actually, and the M stars are the, I don't want to break the pattern, but commonest is not a word, so I'll have to say most common. But we're not quite done, and so that's is related to rarity. So for one thing, you might just think that it makes sense that it'd be easier to make smaller stars, which is true. But something else you can actually expand from this is that the M stars last the longest. So because these O stars are actually really big, they sort of like burn through all of their energy really quickly. So the M stars or the O stars are the youngest, and the O stars, well, they could be, new M stars, but they last the longest. So I'll say longest lifespan. Okay, I'll say longest lifespan, and then I'll change this to say shortest lifespan. Okay, so that's in here just to make it also nice. I'll say this is least common. There. So now it's all close to each other. So anyway, yeah. So and all of the other letters in between are similar, right? So, for example, again, what's after O? B is next, right? So therefore, the B stars are a bit cooler, a bit dimmer, a bit smaller, a bit redder, a bit more common, and live a bit longer than the O stars, right? You can keep going all the way down to get to the M stars. And again, this is of the main sequence, right? When you get to off the main sequence, then it's all different and stuff. What I'm talking about stars are just on the main sequence because that's how most stars are. That's they live most of their lives. And so that's kind of the pattern for that. So again, we'll work more with this to sort of see how this works in the categorization of everything for now. But this, I think, is a good kind of overview of how this diagram works and sort of how everything is related and how you can really classify, because all of this is pretty much gotten by the diagram, and you can just sort of see this in the diagram. The only ones that is not is the lifespan thing. That's just something that kind of comes to mind. Mass also comes from this as well, as you may imagine. A star that is bigger has more mass. It's not a perfect match for things. It's a little bit more complicated than that, but it's close. So that also works pretty well. So your wrap-up question is, so I'm actually asking, how would a B star's mass, radius, temperature, color, lifespan, and rarity compare to the sun? Okay, so think about where the sun is on the HR diagram, and think about, okay, if I have a B star, especially let me clarify, a main sequence B star. I'll make sure to change the form before I post this. To have main sequence B star. How would that compare to the sun? Okay, for all of these terms there. And you can think about it based on the diagram and what I've told you about this, and especially here. And you can put that in. Again, you don't have any homework for this, but we are going to get into something homework tomorrow. We're going to get into the life cycle of a star, and also how it sort of moves around on the diagram. Because just even though, the sun is a G2 V star, it won't always be. So that's something that we'll kind of get into, and how things change and how that goes around like that. So, all right, I'm done.